Hey guys, cool. So this and the next lecture that I give are going to be the final ones on chapter 6 material, unless you guys request specific things along the way for exam prep, etc., etc. So let me share my screen. So what I want to go over right now is when you have functions of multiple variables, how do we actually generalize calculus of variations? So what do I actually mean by that? We've been studying integrals, and we're calling those integrals S, which depend on configurations of functions whereby we integrate over all the different arguments of those functions, right? So that's the setup of what we've been studying so far. What happens if I give you the following? So I'm going to have two arguments of a function instead of one, where we now have an integrand that depends on these variables x, u, and then just for simplicity, we're going to have one function y, which now has two arguments, x and u, and this can depend on dy dx, which is again a function of x and u, and dy du, again a function of x and u. Okay, so stuff is going to get super hairy if I don't make the notation a little bit simpler. I'm going to say that y sub x is the same as dy dx, and y sub u is the same as dy du. Cool. So what I want to do is look at, well, what is a functional derivative, calculus of variations of a quantity S where we have dependence on functions that have two arguments. And so this is exactly the setup we're talking about. Maybe we're interested in the same questions that we are with the previous classical mechanics questions we were asking, where we want to figure out what are the extrema of this quantity S. So to find extrema of this, what we're going to do is exactly what we did before, but there's going to be one additional feature. We want to vary y by alpha times x u. So the one additional feature is that this eta times alpha is going to be, alpha a constant, eta a function, but eta is going to be a function of x and u. So what we want to do is exactly the same thing. To find extrema of S, you say, well, we're looking for configurations y that we would plug in and into the integrand L. And when we integrate over both x and u now, we want y to be function such that S is at an extreme value. And doing that basically is saying if we take an arbitrary function eta and we control the presence of that function by being there by alpha, so if we took alpha goes to 0, basically vanishes, we really want any derivatives of S with respect to alpha to be equal to 0, meaning that y was truly the extreme value to plug in, to extremize S. So what we're going to do is impose, again, like we did boundary conditions on eta. Eta vanishes at x1, x2, but also u1 and u2. So if we're, to clarify here, what that means is if we're at x1, so we plug in x1 into eta, for any value of u, eta is going to be equal to 0. If we plug in u1 for any value of x, eta is going to be equal to 0. That's what I mean by eta vanishes at x1, x2, u1, u2. Cool. So what that means is we're going to have the following setup. If we introduce this alpha parameter, which is going to control how much we've actually varied the function y, which is plugged into the integrand L, we're going to get dx, du, L of x, u. y plus alpha eta, y sub x plus alpha eta sub x, and y sub u plus alpha eta sub u. Cool. And so if we take a derivative with respect to alpha, so ds d alpha, that means what we're really looking for is taking partial derivatives of L with respect to alpha. And the thing that's more complicated now about this is, I'm going to drop the second integral sign. We have partial derivatives with respect to x and partial derivatives with respect to u of y to take into consideration now. So skipping a couple steps here, and you can see my first video to see exactly how to do this. We're going to get eta times dl dy plus eta sub x dl dx. But now we're going to get eta sub u dl du. Those are all going to show up. So with those previous, with the previous expression and the last two terms, we want to do integration by parts. It works exactly the same way as what we were doing before. What I mean by that is we're going to have dx du, partial derivative of eta with respect to x, dl dy yx, so partial derivative of y with respect to x. We can transfer the derivative with respect to x over to dl dyx by doing integration by parts, and we get du eta x u dl dyx x u. Evaluate from x1 to x2. Again, eta vanishes whenever x1 is plugged in for x or x2 is plugged in for x, so that goes away. And then we have a minus integral dx du eta partial x partial L partial yx. Cool. So we got eta on its own. You do the same thing for u. Basically transfer the u derivative over through integration by parts. What you're going to get is the following. ds d alpha is going to be equal to dx du eta of xu, and that's going to be multiplying the following expression. dl dy minus partial x, one sec here, dl dy sub x minus ddu of dl dy sub u. Cool. So using the same rationale from before, eta is an arbitrary function. If we're looking for extrema of s, namely which y's do we plug in such that s spits out a maximum or a minimum value for the integral, eta is a non-factor here. It's factored out. Basically, we could plug any eta in, and so for this to be equal to 0, the stuff that's multiplying eta has to be equal to 0. And so we get a modification of the Euler-Lagrange equations, which takes into account that there's actually more than one argument of y, where we could have y derivatives showing up in the expression for. And so this is the modification of the Euler-Lagrange equations that we get. So again, with the first lecture, what we were doing was we were looking at what happens when we have more derivatives of the same variable on y that's showing up in the integrand. And here we're looking at what if we have one derivative, but it could be of many different variables that y depends on. And so, you get different generalizations and different ways of really stretching what you know about calculus of variation by thinking through these problems. Cool. So the last thing we're going to do is we're going to look at one of the book problems, which deals with how do you actually think about deriving the Euler-Lagrange equations when you have multiple functions that show up and derivatives with respect to multiple functions. And so, cool. Looking forward to it.